Hello everyone and welcome back to another supercut concept, this time about implicit differentiation, optimization, and related rates. So implicit differentiation and optimization and related rates, these are really um, the bread and butter of real life application. And typically in tests, you'll see these related with word problems, and you'll find that it's a bit more analytical than with just our standard derivative rules and etc. So, to get to the root of everything, we need to identify first how to do implicit differentiation in the first place. So, implicit differentiation is a type of differentiation where we don't have explicitly stated um, y values, or for example, a function itself is not explicitly defined. And what this means is take into consideration, for example, these two functions y equals 2x compared to um, y over x equals 2. Now, these two, they're you can convert them to one another. However, this side is implicitly defined because it has two variables on one side, and essentially you have to manipulate the equation for you to be able to get a specific variable. For example, I could multiply x to here and then divide it by y and then bring it back here if I want to get the value of x. Basically, implicit is extra steps. Explicit means that it's stated. Explicit is stated, and this also goes with the definition in English. When you say something explicitly, it's clear. It's a clear definition. While implicit, it's kind of implied. And when we're referring to something implied in math, we're basically saying that we have to derive it or we have to work around it. And in situations like this, for example, y over x equals 2, we can easily isolate y. We just have to move this back here, like I said earlier, and then we'll be back to y equals 2x. However, not every situation is going to behave that way. So, for example, let's say I have a function 2xy plus 3x equals 4. How am I supposed to derive this? Or actually, instead of just making this x, let's make this y squared. Y squared. How would we derive this? Okay, now let's say that we're looking for dy dx. Find dy dx. And dy dx means the change in y with respect to x. So, how do we do that? Alright, now if you recall, our notation for derivatives are d over dx. This is for example, x squared. The reason why is because our variable on top is the same as the variable we're differentiating with respect to. The reason why we say with respect to is because we need to have a reference point. For example, in real life situation, when we're talking about let's say a car moving farther away from you, your reference point is yourself. And if you're going to use a different reference point, you need to change, of course, your equation and like basically your basis for how far the car is and etc. Same thing here. If we want to describe the change in x, we need to understand that our reference point is x itself. And in the sense that we're also trying to find the change in y, we need to find the change in y with respect to x, with reference to x. Because we can't say that it's changing if we don't have any basis. So, essentially, implicit differentiation is using d over dx for every single term. And of course, that depends. Right now, we're looking for dy dx, so we are supposed to use with respect to x. And this is going to be the flow of the entire process of solving. So, step by step, implicit differentiation starts with differentiating both sides with respect to x. Now, we're just going to rewrite the equation here. Plus 3y squared and we're gonna put d over dx on the outside. For d over dx. Now this cancels out to 0 because, well, it doesn't cancel out, it just becomes 0 because the derivative of a constant is 0. Now we're going to distribute our derivative. So now we're trying to get the derivative of 2xy with respect to x plus the derivative of 3y squared with respect to x. Now, what's the next part here? Like I said earlier, we're trying to differentiate everything with respect to x, so we're just going to follow the standard rules. Now this calls for the product rule. It's a product of two functions. So we're just going to do the product rule as seen here. So we're just going to multiply 2 on the outside, since we can use the constant multiple rule here. Derivative of the first term times the second. So the derivative of x with respect to d over dx is just 1. So we're just going to remove that, and we're going to make it 1 times y. And we're going to add this to x times the derivative of y with respect to x. Now, y is not the same as x. So we can derive y using the power rule and we'll get 1. However, we apply the chain rule and we have to put y up here. Because y is not the same variable that we're differentiating with respect to. And as such, we need to adjust and make it an explicitly stated variable, just so that we can isolate that later on in the process. And so from here, we can simplify. We'll get y plus x dy dx, and if we times 2 that, we'll get 2y plus 2x dy dx. And we're going to add this part here. Now 3y squared differentiated with respect to x is going to follow the power rule, so that's 6y dy dx. Chain rule after. Now we're going to bring this down. So plus 6y dy dx equals 0. Now what's the next step here? The next step is going to be to isolate every term that has dy dx. So to isolate each term that has dy dx, we're just going to move this this side here, the 2y that, you know, doesn't have anything attached to it. We're gonna move it to the other side, so negative 2y, and we're going to be left with these terms: 2x dy over dx plus 6y dy over dx. Now we can factor out dy dx here, and this will allow us to leave it on the other side of the equation. So we'll get dy over dx times 2x plus 6y minus 2y. And now to just isolate dy dx, we'll get the final answer to be dy dx is equal to negative 2y over 2x plus 6y. And we can simplify this by factoring out the 2. So negative 2 times y over here on the top, positive 2 on the bottom, which makes it x plus 3y. Cancel this out, and we'll get negative y over x plus 3y. And that is our final answer for the change in y with respect to x. Now, this process is going to be very common in related rates. Now, how about optimization? Okay, so optimization is different from related rates. Optimization involves maximizing and minimizing a function. Now, to isolate a certain variable, let's just use everything in terms of L. We just have to use the constraint and then, well, isolate the variable itself. So if you want to determine width in terms of L, all we have to do is isolate it. So we're going to move 2L to the other side, which gives us 2W is equal to 104 minus 2L. And you want to divide everything by 2 so that we don't have any more 2 here on the left side, over 2. So now we can say that our formula for area is going to be equal to the length times 104 minus 2L over 2. And we want to maximize this function. And the way to maximize is to use optimization. Well, obviously, we're dealing with an optimization problem, so we're going to use optimization to maximize. What I meant to say was we need to use differentiation. An A function is maximized or minimized when their slope is 0. For example, here at this peak, the tangent line has a slope of 0. In other words, the y prime is 0. Same thing with the minimum. It's also going to be equal to 0. So, we're going to get the derivative of this function, and we're going to equate everything to 0. So let's derive. But first, we need to simplify our equation. So we're just going to distribute the L, so that becomes 104L minus 2L squared over 2. And now we're going to get A prime. Now, A prime of x is going to be given by the quotient rule. Now, we're given a constant on the bottom, so let's just go ahead and square that already. The derivative of the numerator is 4L minus 104. And this is actually already our derivative, because the other part of the quotient rule will just end up giving us 0, because the derivative of this constant is 0. So this is now our this is now our derivative for area. Now, from this derivative of area, we want to equate this to 0, because we want to find out the maximum. So we're gonna equate that to 0, and we're just going to use algebra to isolate L. So we'll just remove the 4. This is basically gone already, because 4 times 0 is 0. Then 4L minus 104, so we're going to move the 104 to the other side here. Divided both sides by 4. And we'll get 26 meters as our maximum length. Now, using this value, we can go back to our original function and plug in 26. Now, I currently don't have a calculator, but I will get one right now. I will just put values here. So, for the maximum, we're going to be using 26, and this is going to be 2 times 26 squared over 2. Now, putting that into the calculator, 26 squared times 2. Okay, negative 1352 plus 26 times 104 divided by 2. So that should be, according to my calculator here, 676. Although let me double check. 676 square meters, or meters squared. And that's pretty much how you're going to optimize that problem. So again, let me just double check if I plugged in my values correctly. So 104 times 26 minus 2 times 26 squared divided by 2 is in fact 676. So we can finally say that the maximum area would be 676 square meters. Now, this is one example of optimization, but the process that we did is essentially the same for almost everything. All we have to do for optimization is identify what do we know for sure, like we did here. So, for example, we know for sure that we have 104 meters of fencing. We know that for sure. That means that once we know the shape of the object, we know that our constraint is the perimeter. We know that all of the sides have to add up to 104. So all we have to figure out is, hey, how many sides do we have to deal with here? And once we isolate that using length and width, for example, we pretty much figure it out. And it's also important to use logic here, because actually what we could have done here is, we know that the area is maximized when length and width are the same. The area of a rectangle is maximized when it's a square. So simply making sure that our values here is just L squared, for example, well, not exactly, it's somewhere similar to that process essentially, but making sure that they're equal will basically get us the same answer. So it's an analytical approach to finding the best maximum or minimum that you can get for a certain situation. Now, this was regarding optimization. And again, optimization, basically get the constraint, get the formula you need, derive, equate it to 0, and then see which one is your maximum. Now, how about related rates? I introduced to you guys the optimization to show the difference between that and related rates. Okay, so related rates is calculus heavy. In other words, we're dealing with more aspects of calculus now. More things are changing. Particularly because the name itself of these types of problems involves multiple rates of change. They're all connected to one another. So take into consideration this problem right here. Now, the question states, an airplane is flying towards a radar station at a constant height of 6 kilometers above the ground. If the distance s between the airplane and the radar station is decreasing at a rate of 400 kilometers per hour, when s is equal to 10, what is the horizontal speed of the plane? So, first step, like we did in optimization, is to draw the problem. So we know that an airplane is flying, so it's high in the sky. This is the airplane, and it's 6 kilometers from the ground. So 6 kilometers. Now we also know that there's a distance between the airplane and the radar station. So the radar station is on the ground as well, obviously, and this distance here is s. And we also know that there's another distance here, which is x. We'll just call this x, and we'll make this y, just so that it's simpler for us. Now, we have a right triangle here. So, when s is equal to 10, or let's just label this as 10 kilometers already, we can actually figure out what the value of x is. So, how do we figure that out? Using the Pythagorean theorem, right? But before we get to that point, I just want to show how different this is from optimization. In optimization, we try to find the best value for the maximum or minimum to appear. Now, what does that mean? Basically, we're finding the best derivative, for example, like the best value of the derivative that we can use, or we can plug into the original function so that we can get the best outcome. In related rates, we're trying to find a value that is missing. It's inherently missing. And we're trying to find, for example, in this situation, horizontal speed. We're trying to find the inherently missing horizontal speed despite everything else being given. For example, it says here that the distance is decreasing at a rate of 400 kilometers per hour. That means that the distance, s, with respect to time, is decreasing at 400 kph, or km per hour. And that's a rate that's given, right? And we also know that y isn't changing, so dy over dt is not changing because it's constant. And related rates really uses these values more compared to optimization, where we're trying to figure out the value. This one, we're just trying to reveal what's missing. Anyway, back to what we were doing. To find out what x is, we just need to use the Pythagorean theorem. And the Pythagorean theorem is a squared plus b squared equals c squared. But since our c squared here is s, and we have a value of s, we can just plug in. So we'll use x as our a. So x squared plus 6 squared is equal to 10 squared. And simplifying this should get us 8. Because this will be 100, this is 36, 100 minus 36 is 64. Now, we know that x is equal to 8. Okay. So, how do we move forward from here? We're going to store that for later. We know that at this point in time, this situation right here, x is equal to 8 kilometers. Okay, so now we have to figure out a formula, just like in optimization. You have to figure out a formula that will guide us to getting the correct answer. So the formula that we need to use here is still the Pythagorean theorem. The logic for that is, as one side gets smaller, definitely another one will get larger. So for example here, if I shrink this this length here over at the bottom, x, and I keep the height the same, then my hypotenuse will get a bit more squished and it will get, well, steeper. And that type of logic basically is how we do questions like this. So we're going to use the equation x squared plus y squared is equal to s squared. And we're going to differentiate both sides with respect to time, because our question here is horizontal speed, and speed is defined by time. So we're going to differentiate everything with respect to time here. So d over dt. Now, if you recall, this is the start of implicit differentiation. So we're going to distribute our derivative. So x squared, we're going to derive x squared, which gives us 2x dx over dt, plus 2y dy over dt is equal to 2s ds over dt. Now, we know that all of these can be simplified further, so we're just going to use the simplified version, which is just x dx over dt plus y dy over dt and s ds over dt. So from here, we have to identify what we're looking for now. We're looking for horizontal speed, so we're looking for x, the change in x, and the change in x is dx over dt. So that is what we need to isolate. Okay, we also know the values of dy dt, we know the values of ds dt. So what we're gonna do now is we're just going to plug in our values. We know that x is 8, so we're just gonna put that in here. And we know that y is equal to 6, but dy dt is equal to 0, so this will end up becoming 0 instead. So we're just gonna remove that. So 8 dx dt is equal to s, which is 10, and the rate of change of s, which is given 400 kilometers. Now it's going to the left, so we're going to make it negative. Okay, the reason why we're going to make it negative, and the reason why we can describe it as negative, is because it's going towards the radio station. So my apologies, I forgot to specify that earlier, but just as in physics, when we're going away from the y-axis, this is positive. When we're going towards it, we're going negatively. So that's the explanation for why it's negative. But anyway, after this, you're basically just going to divide both sides by 8. So negative 4,000 divided by 8 is equal to negative 500. And this is our dx over dt. Now what's our unit? According to the given rate a while ago, it was kilometers per hour. So our horizontal speed when s is equal to 10 kilometers is negative 500 kilometers per hour. Now let's try another question. Our final question actually for this supercut video. This one is a combination of multiple concepts. Well, there's triangle similarity here, there's also implicit differentiation, and pretty much very similar to what we just did now. Okay, so now imagine that a light is on the ground 20 meters from a building. Let's use a different color this time, let's use yellow. So the light is over here, and there's a man that's 2 meters tall, and the light is 20 meters away from a building. So this is 20 meters, and we're gonna connect them by a line. And the light is shining at the guy. We're trying to find the length of his shadow on the building when he is 14 meters from the building. So this distance here should be 14 meters. This guy is 2 meters, and this is, well, let's just call it x. Well, we do know that it's supposed to be 6, but let's just call it x for now. Okay, so from here, what do we have to do first? First, we have to label everything that we need to find, and we need to label everything that we're given. So the given that we have is the distance here, which is pretty much x total. We can just call it, well, yeah, let's just leave it at 20 meters. And we need to look for y, because we are also looking for the change in y, particularly with respect to time, because we're looking for the length of the shadow and how fast it's changing on the building. This is the building itself, so we're concerned with y and dt, or the change with respect to time. Okay, so now we also know that this guy is walking this way towards the wall at 1 meter per second. So we know that dx over dt for this guy is 1 meter per second. Alright, so we have pretty much most of our given. Oh, it's also important to know that we know that this is 6 meters. We're not gatekeeping anything. We're just reserving that so that it makes more sense when we bring it up. Anyway, now we have to go part by part in terms of this triangle. This triangle is the only thing we can work with here. So if it's the only thing we can work with, we kind of don't have a choice other than to find its individual parts. And how do we do that? We use triangle similarity. So we can use triangle similarity here by comparing these sides, this combined side right here, this one here, and the small side of the smaller triangle. So basically 20 meters and 6 meters. And we can also compare this height 2 meters to y. Now the reason why we're not going to be using 6 meters immediately is so that we can have a definition of x. Okay, so okay, no, actually I'm gonna leave it here, but just remember that that's the reason why we're not going to be using it for this portion. Okay, so when we're going about proportionality, we want to use same sides over same sides. So x over 20 is equal to 2 over y. It's important that when using triangle similarity, you're going to use parts of a triangle that are different from the triangle that you're already referring to. In other words, this base that I used here, x, should be different from the base I used here at the bottom, 20. Anyway, from here we can simplify and we can get a value of xy which is equal to 40. But then again, we know that x is equal to 6, so we can divide this by 6, which is 40 over 6 or 20 over 3. So that is our y value. Okay, so now similarly, just like how here I said a while ago that as one value changes, the other one will change, thus related rates. The proportionality of these triangles are our basis for how we're going to be able to determine the change in the speed, or the speed, yeah, how to determine the speed of the length of his shadows, the speed of the change of the length of his shadow on the building. That means that we have to use this formula here, and we're going to differentiate this with respect to time. Again, why do we use this? It's because the proportionality is what makes sure that the change in the shadow, for example, will be the same and constant as, for example, one side is changing. And yeah, so we're gonna differentiate both sides. This is gonna get to 0. Product rule, we're gonna get y dx over dt plus x dy over dt. And now we can actually plug in our values. So again, we know our y is equal to y is equal to 20 over 3, and we know that x is equal to 6, and we also know that based on the given we have a dx over dt of 1. So dx over dt equals 1. And what are we required to find? We're trying to find dy over dt, the speed of the change of the shadow on the wall. So we're gonna plug in our values one by one. So 20 over 3 times 1 plus 6 dy over dt. Now we're just gonna equate it to 0. Basically, we're gonna get 20 over 3 is equal to 6 dy over dt. And simplifying once more, we're going to get 20 over 18. This is from dividing both sides by 6. And this will also equal 10 over 9. And this is meters per second. So that is how... Oh, we also forgot that we need to change the sign. Negative here, negative here. There. Okay, so that is pretty much how our related rate for this one will go. Now the question is, why is it negative? Well, he's moving farther away from the light source, so the shadow is going to become shorter. Shorter on the wall at least. Now, that's one way to evaluate your answer if it's correct, because sometimes the sign will actually tell you if it's correct or not. And yeah, so to summarize this video, implicit differentiation, basically it's how to differentiate a function in two variables. Now, always identify first what is the variable that is going to be differentiating with respect to. In other words, what's the thing in the denominator? Is it dx? Is it dy? Whatever. Most of the time, they're gonna ask you, find dy over dx, or find y prime. Y prime means that it's the change in y. So this is basically the same. These two are equal. So if you find yourself in situations where you need to look for the derivative of an equation with two variables, this is essentially how you do it. Now, implicit differentiation takes a lot of practice. So if you're not very familiar with it, I suggest that you do take some time, do some simple problems, even once without chain rule, product rule. Just familiarize yourself with the flow, because problems like this are actually on the simpler end. It gets a lot more complicated when you add sign and etc. But once you're able to do this, you're able to understand questions like this even more. And for some, maybe you might think that this is easier because there's a lot more values to plug in. It's also important to understand that the groundwork for these topics is implicit differentiation. And again, for this one, optimization, basically also another type of related rates, but instead you're trying to find a certain value, as opposed to related rates where you're trying to find a value that's already there. The value that you find in optimization is independent from the stuff that are already defined, other than the fact that there's a constraint. While in related rates, the changes of certain values, like for example here, the change in the guy's movement or the change in the guy's position with relation to time or his speed, that affects the speed of his shadow changing. And for the one on top, when the airplane is moving to the left, that also affects the horizontal speed of the plane. So that's pretty much how they all tie in and they compare with one another. So overall, I hope this video helped, and if you guys need more practice on this, let me know in the comments. Subscribe please if you haven't already. There's more videos, particularly within the next months. I'm going to be focusing on physics. Physics 2, particularly electronics. So if you don't want to miss out on that and you want to learn more about that topic, make sure to subscribe and comment also what topics you guys want me to cover in case that there's anything in school or whatever that you guys need me to help you with. So thank you everyone, and I hope everyone has a great day ahead. Thank you and goodbye.